Okay, well, we almost had a microphone. We were very close to having a microphone, which would have been easier for you to hear me all, but there was some kind of feedback problem. We'll hopefully have a microphone by next Tuesday. So just bear with me for one more lecture, and then hopefully you'll get some amplified sound and you can hear a little better. Oh, I also have another friend I brought with me. It's a pencil, so there'll be less scribbling today, or scribbling out. There'll be more erasing, but less scribbling out. So I wanted to just kind of go over what we learned last time quickly, and then finish our lecture on gradient descent. And then we're going to move forward to subgradient method today. So last time we talked about gradient descent. It was this algorithm here that you've seen now a bunch of times. We want to minimize an unconstrained convex differentiable function, so we just repeatedly move in the direction of the negative gradient. That's what we learned last time, and we also proved that under two different conditions, each of which had to do with how we choose these step sizes, t, we get this 1 over k convergence rate, which means that after k steps, or something like how far we were at the start divided by k away from the optimum in terms of our function value. So there was actually some people who were confused about backtracking. I got some emails and some people asking me about it. I think the main source of confusion was that there was two parameters here. Or some people didn't like the fact there were two parameters. It was maybe felt like too much. So I just actually, in this slide, I corrected the slide and I fixed it so that alpha is a half. So from now on, if you're more comfortable with that notion, for the rest of the class, we can think of backtracking as only having one parameter, beta, and we can let alpha just be a half. So it actually makes the proofs a little easier. I don't think performance differs very much by taking alpha equal to a half versus choosing alpha adaptively. Your book, this Boyd and Vandenberg book, it actually recommends choosing alpha smaller than a half, but let's just say for simplicity, we're going to take alpha equals a half from now on. Okay, so this is the backtracking exit condition right up here. Other questions about that? Okay. One more thing we saw, which I went over kind of quickly at the end, I want to just reiterate because it's going to come up on your homework, and also it's an interesting point, is that if we're just looking at doing linear regression, so that would be our f up there, we can do this thing called forward stagewise, which is a statistical procedure that's pretty natural, where we start with the coefficient vector being 0 as our guess. In order to get the least squares solution, we look at the variable that's most correlated with the residual and absolute value, and we add a little bit of the sign of that variable to x, to that component of x. Right? So if the ith variable is most correlated with the residual, then we add a bit to xi, and that's our new guess for the coefficient vector x. And if we did this enough times, this would give us the least squares solution. But if we do this only a handful of times and we stopped, then it gives us something that's sparser than a least squares solution. That's called forward stagewise regression. And I also talked about this thing called steepest descent, which is like gradient descent. It's very similar, except for it uses a different norm underlying the idea in terms of which direction you go. So the updates are like this, very similar to gradient descent. The next update is equal to x plus t times delta x, where delta x is chosen through the following steps. First, we look at the point that's, when I take the inner product with the gradient, it's the smallest over all vectors that have unit q norm for some q. Okay, so if q is equal to 2, then I would take v just to be equal to the minus gradient over its norm. So this would be the normalized gradient descent step. Then the second step just scales that back up, because it has unit norm according to some norm, the q norm. So this is just a scaling step, because it wants to respect the fact that if the gradient is large, then we'll take a bigger step. That's it. So gradient descent is this particular method when q is 2. It's a special case of steepest descent. And we also looked at the case when q was 1, and I claimed that this was true. You can go home and check this. Today we're going to actually learn subgradients, so we're going to be able to prove this more rigorously. That if q is 1, then the vector that minimizes the inner product with f, subject to having the 1 norm smaller than or equal to 1, is just the following. I take the ith standard basis vector, I multiply by the negative ith partial derivative of f, where I is the component that's biggest in absolute value. Okay? So this is actually a subgradient of the infinity norm of the gradient of f. So we're going to learn that today, I guess more rigorously, why this is true. But you can kind of see why this is true intuitively, just based on maybe reasoning that if I only have a certain amount of slack in terms of how much I add up to 1, then I'll just take the largest component if I want to make that the smallest. So normalized steepest descent is what we do when we don't include this step here. We just take the descent direction to be this u. So we're going to make it have unit norm according to whatever the underlying norm was, the q norm or the 1 norm. What we saw was that normalized steepest descent with the 1 norm was exactly forward stage-wise regression. Okay, they're the same thing. We just call them different things depending on what field we are studying. And the curious thing about this is that if you were coming from an optimization point of view, you would never think that it would be a good idea to stop one of these descent procedures early, because the point is to go until you get the minimum. Right? You don't want to under-optimize. That would seem like kind of a foreign concept. But it's connected to this forward stage-wise idea where it's very natural to stop the procedure early, because that gives us a sparse estimate. And what we saw was that actually that sparse estimate is very similar to the lasso estimate, which we studied before, and we'll continue to study throughout the course. And here's just a picture of that. On the x-axis, I've plotted the lasso bound for the L1 norm. And each of these red curves here is one of the components of x as a function of that bound. So these are the lasso solution paths as I vary the bound. This is the forward stage-wise path for a very small value of that, for this very small value of this gamma parameter here, this learning rate. And they're very similar. I mean, this has a little bit more of a jigsaw blocky pattern, but you can prove that for some instances of y and a pretty broad class of these actually, the limit of this process as I take the step size smaller and smaller is exactly just the lasso solution path. So that's a nice kind of, I guess, a fortunate coincidence, because this is a very simple algorithm. You can all code this up no problem in maybe 3 or 4 lines, and yet it gives you the solution path to a pretty complicated optimization problem. And on the homework, you're going to be looking at something that's even more complicated than the lasso, but you're just going to apply this forward stage-wise idea, and you're going to see that it has effects like the regularized version would. Other questions about that? Yeah, this is just, so, goodness, I always try to zoom in. This picture is taken from a textbook, and in the textbook they chose to call the components alpha instead of x. So for us, this would have been the sum of xk, the absolute value of xk. That's it. Any other questions? Okay, so there's a couple slides on gradient boosting. For the sake of time, I'm not going to cover that. That's another connection to statistics. I encourage you to read through that because it's an interesting topic, and boosting has become quite a popular field in the last maybe 10 years or so. And gradient descent plays a very big role in understanding why boosting works. They're very intertwined. So I'd recommend that you read that for your own interest, and then you can always ask me questions or Jeff or one of the TAs about that in our office hours. So we've established that gradient descent under a Lipschitz continuous on the gradient gets this rate 1 over k rate. That's what we proved last lecture. Okay? And gradient descent is an example of something called a first order method. So what does that mean specifically? That means that it's an iterative method. So it actually does what we do where we guess x0, x1, x2, x3, etc. And each update is allowed to update x within the span of the gradients it's seen at the previous iterates plus the initial point. That's what a first order method is. Okay, each update must lie in this affine set right here. So why is gradient descent a first order method? I mean, you can think about it like induction, right? So gradient descent surely lies in the span of the gradient of f at xk minus 1 plus xk minus 1, right? But here we've actually restricted it to having x0 and all the other gradients, so we can just kind of think of inductively, well, xk minus 1 was in the span of all the other ones, etc. So gradient descent is actually one of these methods. It's a first order method. Okay, so this is a class of problems we're going to be interested in for the next 3 lectures. And we got this 1 over k rate for gradient descent. So you might ask, how good is that? Is there another first order method, a modest method that only uses gradients that we've seen so far and the initial guess that does better than gradient descent? Is 1 over k competitive or not? And there's a theorem by Nesterov that says that for any k that's smaller than or equal to about half n, and any starting point, x0, I can always find a function in this problem class, the problem class being functions that have Lipschitz continuous gradients, such that any first order method that we look at, doesn't matter whether it's gradient descent or otherwise, it takes at least on the order of 1 over k squared steps. Okay? So the lower bound is an order of magnitude smaller than what we got. We got 1 over k, and this basically tells us that for the problems that we're interested in, that we can prove something about where the gradient is Lipschitz, nothing can do better than 1 over k squared. And I think actually you're going to prove that on your homework. That's one of the questions. So now you might ask, well, can we achieve a rate of 1 over k squared? Right? This guy thought of a theorem that says, well, you can't do better than that, so can we get to this optimal rate? And the answer is yes, we can. And actually even more. We can do even more than that. And we're going to see that next week. I'm sorry? N here is the dimension of the space in which x lies. A little bit of a technical issue here. Yeah, so n is just x is a vector in Rn. That's it. Other questions? Okay, and for all my lectures, at the end of the lecture, I'm going to have a bunch of references. People were asking me last time about where I got some of these theorems, or I was mentioning also stuff like in your book it shows blah blah blah. So you can look here at the references if you're interested in reading more about what we've learned. It's always good to kind of read it from a different perspective. I think it helps clarify things. Okay, today, subgradient method. So I'm not going to go through the intro slide because we just covered that again. But there are 2 problems with gradient descent, right, that we've pointed out. One is that it's slow. It doesn't do particularly well, at least compared to the lower bound of 1 over k squared. It's getting a rate of 1 over k, which can be a very big difference in practice. The other is that it doesn't work for non-differentiable functions, right? We had to assume that f was differentiable in order to use it. So we're going to talk about this next week, and today we're going to talk about the non-differentiable case. Okay, so here's today's outline. How many people have learned subgradients in a previous class? Okay, so not very many. That's okay. We're going to have a pretty thorough introduction to it, but I guess I would have gone faster or slower depending on how many people have seen that. So before we talk about subgradient method, we have to learn what a subgradient is. And basically it's a way of dealing with convex non-differentiable functions and enjoying the properties of a differentiable convex function through kind of a little bit broader notion. And that notion is called a subgradient. So remember that we saw that for a convex function, its gradient is always an underestimator in terms of the tangent line. Right? If I draw the tangent line to f at x, for a convex function it always underestimates the function. So for any y, it's larger than or equal to f of x plus the gradient of f of x, inner product with y minus x. That was a property of convexity. So a subgradient is a very similar notion. If f is not differentiable at x, then we define a subgradient of x to be a vector g that's in the same dimension as x. So it's the same dimension as the gradient of f of x if f is differentiable. That gives us this linear underestimation. Okay, so it's any vector g that satisfies f of y larger than or equal to f of x plus g transpose y minus x for all y. So that's a subgradient at x. It gives us that property that we know holds because of convexity if it were differentiable. Okay, so what are some properties of subgradients? One is that it always exists. So here I'm not being incredibly rigorous because I haven't told you what the domain of f is. In all of the lectures that yesterday's lecture and the next three, I'm not going to really worry about the domain of f. I'm going to just assume the domain is all of Rn. In cases where the domain is not all of Rn, you're going to kind of know when things go wrong, and then there are kind of subtle corrections you have to make. But for the sake of simplicity, I don't want to kind of worry about those special cases. So within the relative interior of its domain, and we're going to assume the domain is all of Rn, subgradients exist for convex functions. They always exist. If f is differentiable at x, then there's only one subgradient, and that subgradient is its gradient. Okay, that's another property. And another property is that actually the same definition works for non-convex f. If we have a non-convex function, we can still talk about its subgradients, and some of the things that we talk about will still be true, but we don't know that it's always going to exist. Okay, so what's an example of a function that's differentiable but not convex and doesn't have a subgradient? Can you guys think of one? Yeah, that's a good example. So any concave function, right? So there's not a line I can draw there with a certain slope that will underestimate the function everywhere. Okay, but it can also be something like that, right? There's no line at this point that's going to underestimate the function. So non-convex f can have subgradients, but we don't know they always exist. So we're going to just think about convex functions, as usual. So let's go through some examples. Let's look at the absolute value of x. This is something that we are going to kind of revisit a lot. It's something we're going to use as a penalty a lot through the class. So it would be good to understand what its subgradients are. So if x is strictly larger than 0, or strictly smaller than 0, it's differentiable, right? It's just linear in both those parts. So its subgradient is just equal to the slope of this line, which is the gradient, uniquely. Okay, so for any x not equal to 0, there's only one subgradient, and that's the sine of x. That makes sense? How about at 0? Well, at 0, it's not differentiable, and it has many subgradients, and actually, it's the slope of any line that underestimates that function. So the subgradients at 0 are any elements of this interval -1 through 1. Okay, because if I draw a slope, a line of slope g through 0, for any slope between -1 and 1, it's going to underestimate that function. Okay, is that clear? Yeah? Okay, so here's another example. We're going to a little higher dimensions. Let's take the Euclidean norm. So this is just the sum of the squared components of x, and I take the square root of that. Right? That's differentiable everywhere except at the origin. Okay, so this is what it looks like in R2. It's smooth everywhere except for at the origin. So if x is not equal to 0, then there's a unique subgradient, and it's equal to the gradient, which is x over its norm. If x is 0, then the subgradient is any element of the unit ball. Okay, because if I take anything larger than anything that has norm larger than 1, I'll get some kind of plane that doesn't underestimate this function. Okay? Let's look at the absolute value of x when I add it up over components, or the L1 norm. This is what it looks like in 2 dimensions. So it's not actually differentiable for every x except for 0, because it has these lines here, these kinks where it's not differentiable along the coordinate axes. So there's even more special cases for this function. If the ith component of is not 0, then the subgradient has a unique ith component, and it's just equal to the sine of the ith component. Okay? But if the ith component is 0, so if we're on one of these coordinate axes, then it's like the one-dimensional case. It's any element between -1 and 1. Questions about that? No? Okay, what if I have 2 functions? I just have 2 convex and differentiable functions, and I consider the maximum between those 2 functions. That's my new function. So f of x is the maximum, the pointwise maximum of f1 of x and f2 of x. Then in all spots where, let's say, f1 is bigger than f2, so maybe in this region right here, there's a unique subgradient, and it's equal to the gradient of f1 of x. In all spots where f2 is larger than f1, there's also a unique subgradient, and it's equal to the gradient of f2 of x. Now how about the x at which they're equal? Well, actually, then a subgradient is any point on the line segment that joins these two gradient vectors. So here's what it looks like in 1D. In this region, right, I can take the slope, and that's the unique subgradient, and same here. Here, it's anything between the limiting left and right slopes. It's anything in that interval. Okay, because anything there is going to underestimate the function. So what's a subdifferential? A little bit more of nomenclature. The subdifferential is the set of all subgradients. Okay, so that's denoted by the partial of f. It kind of looks like a derivative, but it's a set. And it gives us all g, such that g is a subgradient of f at x. So one thing is that it's a closed and convex set. Okay, that's true even for non-convex x. For non-convex f. It's not empty. We know that's true for convex functions. It has at least one element, but it can be empty if f is non-convex. If f is differentiable at x, we already know this one, then the subdifferential has one element, and that's the gradient. That's all it has. And conversely, if it has only one element, then f is differentiable at x, and that element is this gradient. Okay, so it matches kind of all of our intuition in terms of the differentiable case, just generalizes this notion to containing multiple candidates, and those candidates are the subgradients. Okay, so I think there's a neat connection between subgradients and convex geometry, and a lot of these things that we see are going to be useful when we deal with constraints. So let's suppose that I have a convex set C, and I'm considering an indicator function, I of C, and this is something that this notation we'll use throughout class. I of C is just the indicator that x is in C. So it's 0 when x is in this convex set C, and it's infinity when it's not. Okay, so convince yourself that actually is a convex function. And one nice thing about using indicators is that if you ever had an optimization problem that was constrained, I want to minimize f subject to x being in this convex set C, so this could enforce x to satisfy a bunch of inequality constraints and equality constraints. That's the same as minimizing an unconstrained problem where I just add that indicator. The indicator is just added to the criterion, and it gives me 0 when x is in the set and infinity when it's not. Okay? So what are the subgradients of this indicator function? That's a question you might ask. It's a convex function. That's perfectly legitimate. And actually the interesting connection is that the set of subgradients, or the subdifferential of this indicator function, is exactly the normal cone to this convex set C at the point x. Okay, what does that mean? That's the set of all g, such that g transpose x is larger than or equal to g transpose y for all their y and c. So x maximizes the inner product with g over all vectors in that convex set C. So why is that true? Well, we can just go right back to the definition. Right? G is a subgradient at x if it satisfies this inequality for all y. The indicator function at y has to be bigger than or equal to the indicator function at x plus g transpose y minus x. So if y is not in C, right, then this is infinite. So that's fine. That inequality is satisfied for any g. And if y is in C, then this condition reduces to 0 being larger than or equal to g transpose y minus x. Right, so if we rearrange that, it just gives us this exactly. So here's a picture of that. Let's suppose this is my convex set C. Okay, the indicator function is something that's 0 when I'm inside C and infinity otherwise. Then if I ask you what a subgradient is at any point in C of the indicator function, you have to just look at the normal cone to the set at that point. So right here, there's only one subgradient, and that's this vector here. Right here, again, there's only one subgradient, and that's this vector. But over here on this corner, the normal cone is a cone. That's why it's called the normal cone. And it contains all vectors in the shaded region. Okay, so for any vector in the shaded region, the inner product of that vector with this point is largest over all other vectors in this constraint set C. Okay, so it's a nice way of just kind of reading off what subgradient should be if you have an idea of what the constraint set looks like. It can help with your intuition. People have questions?
So the normal cone with an interior point, is that empty?
There's the normal cone at every interior point is empty, yeah.
But the subgradient is 0 at any interior point.
So I guess the normal cone actually always contains 0 because it's a cone. So the normal cone is the set containing 0. And so is the subdifferential.
The other thing is that it's not just one subgradient at this point, right? It's an entire array of subgradients.
Yeah, that's a good point. So Jeff raised the point that whenever you talk about a cone, it's implicitly, when I have these arrows here, it's any vector that's along this line. So there's not just one subgradient, it's anything along this line, it's anything within the shaded region if I imagine it extending out infinitely. Okay, so how do we deal with subgradients just like we deal with gradients? Well, there's subgradient calculus just like gradient calculus. A lot of the rules are very similar. I think these rules are extremely useful to know because computing subgradients from the definition can be a pain. It can be really hard and really tedious. But if we know the subgradients of, say, a handful of things, and then we use these rules, we can compute the subgradients of a lot of different functions much more easily. So scaling, if I have a function f and I multiply it by a positive real number, then its subdifferential is just a times the subdifferential of f. So why does a have to be positive here? Right. If a is negative, then this might not be this will not be a convex function if f is convex, right? Unless it was linear. Addition, if I have f1 plus f2, the subgradients of that new function is just the sum of the subgradients. Okay? So these two are sets. So I mean that I take any element in this set and I add any element in that set and it gives me a subgradient. How about affine composition? What if I take a new function g that's defined by f composed with some affine function? I'm sorry, that's a typo. This should be g of x equals f of ax plus b. Okay, so you might ask, what are the subgradients of g? Well, it's just like the chain rule for differentiable functions. Right? I have to multiply by a transpose. And then a transpose times any subdifferential of f at the point x plus b is a subgradient of g. Okay, so again, this is a set, so this means I take a transpose times any point in that set and it gives me a subgradient. Okay, so these should all look familiar from the chain rule and from calculus rules for gradients. This one's a little different, this next one. If I have f being equal to a max of a bunch of convex functions pointwise, let's say I have m of them, then the subdifferential of f at x is a little bit complicated to write down, but in terms of understanding what it is, it's very simple. I look at all the functions that are active at x. That means these are all the functions that have a value that's equal to the maximum. Right, so if I'm taking the maximum between m functions, maybe one or two of them could achieve the maximum at a particular point. I look at all those functions. I look at their subdifferentials. I take a union of that set, and then I take the convex hull of that, because this union might not be convex. Okay, so that gives me any subgradient at f. So just for...
So on the previous slide, you had when you did the subgradient of the max of f1 and f2, there's a line. Is the line segment joining f1 and f2?
Yep.
Line? So you have line.
Oh, sorry. This should, you're right. So this should be the line segments joining f1 and f2, the gradients of f1 and f2. So it's a special case of this rule. Thank you, Shiva. So if I just have two functions, right, and they're both maximum, they both achieve the maximum at a point x, then this rule is a special case of the rule I just wrote down. What's the convex hull of 2 points? It's just the line segment joining those 2 points. Okay, so there should be a word segment in there. And generally, if I have m functions, this is what it looks like. Other questions about that? Yeah. So the next slide, we're going to talk about the infinite case. That was a prescient question. So what happens if I just take the max over a bunch of functions that are indexed by some set S? Okay, then under some regularity conditions on S and F for that set, I have to put a little more conditions on them. I think sufficient conditions are that S is compact and that F is continuous both in X and in S, this index. But I think those are not necessary, but they're sufficient. Then the subdifferential of F at X is equal to the same thing, but I have to put a closure on top of this now. Okay, so I just look at all the functions that achieve the maximum at X. I look at their subdifferentials. I take the union of all those different subgradients. I take the convex hull of that, and I take the closure of that. That gives me the set of subgradients of F at X. So this is a very, very useful rule for one important special case, for other cases too. But there's a very important special case when it comes to norms. Okay, so if I look at the LP norm of X, okay, what is that? That's what happens when I raise every component of X to the P, and then I take the 1 over Pth power, I have to add them up. One way of defining its dual norm, I claim that its dual norm is something that satisfied this, 1 over Q plus 1 over P equals 1. Another way of defining its dual norm, maybe we'll give this to you as a homework problem, is that I can write this as the max over all y that have Q norm less than or equal to 1 of y transpose X. Okay, so that's how we define dual norms in one way, and it turns out that actually this is the same condition here. Okay, so this is an alternate definition for norms. So look, this actually fits this exact same prescription as up here. I can define f of x, which in this case is the p norm of x, as the maximum of a bunch of linear functions over the set with bounded q norm, with unit q norm. So what are the subgradients of this function here, the p norm? Right, we had pictures earlier where we were trying to kind of guess them based on our intuition. Well, this actually gives us a very specific prescription for it. The subgradients of the p norm are all vectors y that have q norm smaller than or equal to 1 and that achieve the maximal inner product with x over all vectors that have unit q norm. Okay, so I can write xp as y transpose x for some y that has unit q norm. And then the subgradient of this function, well, it's actually, let me be a little more precise here. If that's true, then y is a subgradient of the LP norm of x. Okay, because it achieves that maximum. The set of all subgradients is the convex hull between all such y. But as long as I have one that I know achieves the maximum inner product, that's a subgradient. Okay, so that's a useful rule for kind of reciting what subgradients are of different norms. Questions about that? Okay, why subgradients? Why are we bothering with this concept at all? Well, there's two reasons. The first is convex analysis. So we're going to see, I think in the next slide actually, that an optimality condition for what it means to be a minimizer of a convex function can be characterized via subgradients. Okay, duality also has a very close connection to subgradients. So a lot of convex analysis that we're going to see throughout this class and that you'll see beyond this class, it involves the notion of subgradients. So understanding subgradients allows us to say a lot of pretty powerful things. There's also optimization. It's not only kind of a mathematical tool, there's also an algorithmic advantage that we're going to see later on in this lecture. If you can compute a subgradient of a convex function, then you can minimize it. That's true for almost any convex function. We just have a couple restrictions on the convex function. But once we place those restrictions, it doesn't have to be differentiable. As long as we can compute its subgradients, or a subgradient, we can minimize it. That's pretty good. So here's an optimality condition. It's kind of our first peek at optimality conditions. We're going to get to a suite of conditions called the KKT conditions a little later in the course. But here's our first peek at an optimality condition. If I have a convex function, f, and I want to look at its minimizer, and I claim that it's achieved by some vector x star, okay, that's equivalent to x star being a subgradient, I'm sorry, a little backwards. It's a good thing I brought a pencil. To 0 being a subgradient of f at x star. Okay, those are the same thing. Why? Let's check this really quickly. What does it mean for 0 to be a subgradient? It means that for any y, f of y is larger than or equal to f of x plus the subgradient, which in this case is 0, transpose y minus x. Okay, so if 0 is a subgradient at x, then x is smaller than or equal to y in terms of its function value for every y. So it's the minimizer. Okay, and remember now, I wrote this as an unconstrained problem, but if I have constraints, I can just add the indicator function up there. Right? So if I have this problem, minimize x over c of f of x, I can write that as minimize f of x plus the indicator function of x. Now that's an unconstrained minimization problem, and x star is a minimum if and only if 0 is a subgradient of the sum of these two functions at x star. Right? And from my subgradient calculus rules, that set is just that set. Okay, I can typically compute this, and we know what that is. We actually just described that. Those are all the normal vectors. Okay, so we can also characterize optimality for constrained problems too. So very useful. And when f is differentiable, this is just equal to the set containing the gradient of f at x. Right? So it's the same thing as saying the gradient must be 0. So it extends our intuition for the differentiable case to the non-differentiable case. Yeah, question? The constraint space has to be convex because that's our requirement for convex optimization problems. If the constraint space was not convex, it would not be a convex optimization problem. There's a lot of reasons for that. I mean, for one, if C wasn't convex, then we could write that problem equivalently as this problem, and that criterion would not be convex. Right? So if C is not convex, then this indicator function is not convex. That's one way to think about it. Okay, so let's apply this rule to soft thresholding. I'm sorry, let's apply this rule to a problem that we'll see a lot, which is the lasso problem, but with design matrix A equal to identity. And we're going to see that from this rule we're going to get something called soft thresholding, which will describe the set of solutions to us. So I'm writing down here a problem that looks very similar to the lasso, but it's like I'm doing regression with my predictors being equal to the identity. Okay, I have predictors that are, each predictor is just the indicator vector for that particular component. So you might ask, that's like a really trivial case, why would I care about this regression setup? But this soft thresholding operator is going to come into play a lot. It's going to come into play next lecture and beyond that, so it's important to know. So I wrote the lasso problem previous times as a constrained problem, right? It was subject to x having one norm smaller than or equal to t for some value of t. I can equivalently write it in this form, and that comes from duality. We're going to see that later in the course. But just know that if I have a constraint, I can actually turn that constraint into part of the criterion by multiplying by some non-negative Lagrange multiplier here, lambda. Okay, so that's another way of parameterizing the lasso problem, is letting lambda vary there. Okay, so how do we find out which x star achieves this minimum? Right, well, we actually have a rule for that. We just call this whole thing f. We evaluate its subgradients, and we see when it has 0 as a subgradient. And if it has 0 as a subgradient, that's a minimizer. Okay, so let's do that. So remember, subgradients are additive, so I can look at the subgradients of either part and add them up. So the first part, that's differentiable, right? So its gradient, in this case, is just x minus y. Plus, what are the subgradients of this? Well, I can think of this in multiple ways. Maybe the easiest way to think about this is that, well, this is just the sum of the absolute values of xi as I goes from 1 to n. So again, I can make this additive, right? I can evaluate the subgradient of this function, which is just the absolute value of xi for each I, and add those up. And in doing so, I'll find out that they look like this. I guess I called it S in the slide. So here in the slide I called it S. So everything of this form is a subgradient of f, where S has to satisfy the following criteria. It's equal to the sine of x, I, in its ith component, if xi is non-zero. Otherwise, it's anything between minus 1 and 1. Okay, so anything of this form, where S satisfies this, is a subgradient of our loss function, our criterion. Now we want to find out which values of x give us 0 as a subgradient. Okay, so which values of x can we stick in here and make this 0? So I claim that actually, if I take x star of in this case it's y, which is equal to what I wrote in the previous slide. Sometimes we denote this by capital S sub lambda of y. This is called the soft thresholding operator. Which is defined as follows. Its ith component is equal to xi minus lambda if xi is bigger than lambda. It's 0 if xi is between minus lambda and lambda. And otherwise it's equal to xi plus lambda. Okay, so it takes, I'm sorry, this should all be yi's. It's a function of y. Okay, so it takes y and it tries to shrink it towards 0 by amount lambda. If y is smaller than lambda, if it's already closer to 0 than lambda, then it sets it equal to 0. It's not going to move through 0. Otherwise, it shrinks it to 0 by an amount lambda. So this is a picture of what that function looks like. Right? So if this is y here, this is the line, then I shrink y to 0 by an amount lambda. In this case, lambda is, I think, 0.5. In the case that y was already smaller than minus 0.5, or between minus 0.5 and 5, it sets it equal to 0. Otherwise, it shrinks it to 0 by that same amount. Okay? So now let's actually plug in this proposed solution and check that we can get 0 as a subgradient. If we can, then we know it's the minimizer. Okay, so we have to just look at a bunch of cases, basically. Let's look at the case where a particular component, yi, is bigger than lambda. Okay, in that case, x star I minus yi, right, that was equal to lambda. Okay, and what's the subgradient at x? well, x is equal to the subgradient is just -1 there, right? So in the ith component, it's equal to 0. What's that? Sorry. Okay, so we want to check that the ith component of gi can be made equal to 0 by taking xi equal to this particular soft thresholding operation. Okay, so bigger than lambda we can do that just by definition. Smaller than lambda we can do that by the same argument. If yi is between minus lambda and lambda, then x minus yi, that part's 0. I'm sorry, that's not correct. That part is just equal to yi minus yi, right? Because xi is 0. And the subgradients can be anything between -1 and 1. So I'll just choose it to be yi over lambda. That's a perfectly reasonable subgradient. Okay, because xi is 0 in this case. And I can make that 0. Okay, this is between -1 and 1 if yi is smaller than lambda in absolute value. So I can just go through and I can check in each case that by plugging in this soft thresholding operator, I can actually make 0 a subgradient. And in that case, we know it is the minimizer. Are there any questions about that? Yeah. I'm sorry?
How do you define a factor as -1 in the first place?
Oh, sorry. Let's see. Yeah, the sign is actually equal to 1 in that case. So if xi is equal to yi minus lambda, then it's positive, right? So its sign will be 1. I'm doing something silly here. First lambda should be minus lambda. Thank you. Right. Okay, and this similar argument holds for yi. Smaller than minus lambda. Okay. I'm going to state the subgradient method, and then we're going to take a break, and after we come back, we're going to start looking at it. So now that we've learned subgradients, we can take our idea for gradient descent, and we can just replace the gradient with a subgradient. And that'll give us a new method. That's all that subgradient method is. So it's the exact same thing. We initialize some vector, and then we repeat some iterative step, where we move in the direction of a negative subgradient, now not a gradient. But remember, this is not unique, so we can actually choose any subgradient of f at x and move in that direction. Okay, so gk minus 1 is any subgradient of f at xk minus 1. Why did I call it subgradient method, not subgradient descent? Well, because actually it's not a descent method. It's not necessarily descending, so that's a disadvantage, is that we may actually increase the function value by repeating this update. Okay? So what we do is that we actually keep track of the best x we've seen so far in terms of its function value. So after the kth iteration, I don't just return xk, I return the best out of all the previous k that I've seen in terms of the function value. What are some step size choices? So step size choices in subgradient method are completely different than they are in gradient descent, in that we don't have an adaptive strategy for choosing the step size like backtracking. But actually, they're all pre-specified. So there are several different strategies. I think there's actually 5 classic step size choices, and I'm showing you 2 of them. And you can prove various things about these step sizes, but they're all fixed. They're all pre-specified choices of t. So the first is constant, right? That's an obvious one. Just take it equal to the same thing in every iteration. A second strategy is to choose the step sizes so that they don't sum. That means they're not summable. It means that when I add them up, so this is another typo. So this should say that when I add up their squares, it's finite. When I add them up, they're infinite. So what's an easy example of a step size choice that satisfies that? Louder. 1 over k. Yeah, right. So tk equals 1 over k is a perfectly reasonable choice for that particular category. Okay, so this means that they go to 0 but not too fast. And we're going to see precisely when we prove convergence for this why we want them to go to 0 but not too fast. I mean, it kind of makes sense intuitively. We want them to go to 0 because if they don't go to 0, then we don't want to be taking arbitrarily large steps for arbitrarily large iterations of the algorithm. We want to be able to make precise steps at some point. But we don't want to go to 0 too fast because we want to have some power in making decently large steps throughout the runtime of the algorithm. So this is a condition, this is a way of saying that. Go to 0 but not too fast. So there are lots of other options too, and in fact for other options that I'm not mentioning, the criteria you need to put on F to prove that subgradient method converges is even weaker. So we can prove that subgradient method works under even more broad circumstances with other step size choices. But those proofs tend to be more complicated, so I'm just focusing on these two choices here. And we have some decently restrictive but not too restrictive conditions. Okay. So I'm going to state the theorem, and when we get back, we're going to start proving it. Let's assume that F is Lipschitz. So it's not differentiable, potentially, but it's Lipschitz, and has some constant g. Right? So previously we assumed that the gradient was Lipschitz. Now we're assuming that F is actually itself Lipschitz. Okay, so that's equivalent to saying that its subgradients are bounded by g in norm at any x. Okay, so you can convince yourself that these two things are the same. But saying that F is Lipschitz with constant g is equivalent to that. We're also going to assume that at our first step, we're some finite distance away from x star. Okay, another way of saying that is that where we start, we're a finite distance away from x star. And then when we have this Lipschitz condition, that's implied. Okay, so why this seems kind of like a strange condition, but all this is saying is that x star is not off at infinity somewhere. Okay, it lies within the relative interior of Rn. It lies somewhere that when we start, we can place a bound on how far we are away. So this is a very, very weak condition. Just saying that x star can't be off at infinity somewhere. And let me pull the class. Is this stronger or weaker than the gradient of f being Lipschitz? So if f was differentiable, what do you think would be more restrictive? The gradient being Lipschitz or the function itself being Lipschitz? How many people think the gradient is more restrictive? Okay, and how many people think that the function? Okay, so about half and half. So neither condition implies the other, but for I think a bunch of reasons, the gradient being Lipschitz is more restrictive. It's a more restrictive condition. So let's see, we can think about it in the following way, for example. Any piecewise linear function, so if I have any function that is piecewise linear, that's Lipschitz. I just take the largest slope and absolute value, and it's Lipschitz with that Lipschitz constant. Right, but it doesn't have a gradient at a bunch of points. So it's not even differentiable at some points, so its gradient is not Lipschitz, certainly. Its gradient is piecewise constant, which is not a Lipschitz function, right? Its gradient might look like this, and then that, and this is certainly not Lipschitz here. Okay, so that's a function that's Lipschitz, but doesn't have a Lipschitz continuous gradient. Now let's think in terms of subgradients. What if I actually replace the gradient condition that I have for differentiable functions with subgradients? What if I said that this had to be true? For any xy, if I take any subgradient of the function at x and any subgradient of the function at y, it has to satisfy the usual Lipschitz condition. Right, that's the alternative to what we've written down here, which is Lipschitz on the function itself. Well, that would be no good at all, right? We couldn't make that work with almost any function. Let's look at the absolute value function, for example. Okay, so let's take x equals 0 and y somewhere out here. Okay, the subgradient of this function at y is just 1. The subgradient of this function at 0 is anything between -1 and 1. So if I made it true that any subgradient at 0 minus any subgradient at y had to be smaller than or equal to L times the distance between x minus y, that would be no good. Because, for example, -1 is a subgradient, right? And 1 is a subgradient for any y that's positive. So that's like saying that this has to be smaller than or equal to L times x minus y, which is just y. Right? That's definitely not going to be true for any L fixed. I can take y as small as I want, and this slope and this particular subgradient at 0, which is -1, are never going to match up. So we can't place the same kind of conditions we can in terms of subgradients on the functions. Otherwise, we would basically have to throw out a bunch of functions that we like to optimize. So it's, in a sense, it's a weaker condition, so we can expect a weaker result. Right? It's non-differentiable. We actually put kind of more weak conditions on it so we can expect a weaker result. And here's what the result is. For a fixed step size, the subgradient method doesn't even converge to the optimum necessarily. It gets within g squared times t over 2 of the optimum, where t is the step size. So if I run it forever and ever and ever, we're guaranteed that it gets no more than g squared times t over 2 away from the best. But it might not get the best. Okay, so that's not a convergence result in terms of converging to the minimum, but it's something. For diminishing step sizes, if I choose them according to this prescription where they go to 0 but not too fast, then we can actually prove that it converges to the minimum. Okay, it actually will give us a minimizer in the limit. Okay, let's take a break and we'll get back to how to prove these.